So in the last class, we have discussed this RM1 model. That is when we used this relevance feedback to perform a query expansion. In RM1 model, what we have done is basically we have considered an IID sampling of the terms from different language models, specifically the pseudo-relevant documents, and then we computed their likelihood of being generated from this document. So particularly for a given query queue and a selected set of pseudo-relevant documents, what we have done is we have computed P W comma Q, that is the joint probability of the word occurrence W, together with the query words, query terms, as following an independent and identically distributed sampling. So here, what we have done is basically we have considered all the documents in the pseudo-relevant document set, and we have computed the probability of generation of that term from that document here into the probability of the term of the individual query terms being generated from the document. So in broadly, this is basically equals to, as we are considering a joint probability here, so it is basically probability of W given D into probability of Q1 given D into probability of Q2 given D, and so on up to Qk, probability of Qk given D. Now this we can club together to write as for all the query terms the joint probability of the generation of the individual query terms. Now if we replace this here while computing this joint probability here, we will be getting a formula like this, which was basically the RM1 model. Here this PD is basically the prior probability that we have said that mostly it is considered as uniform, and hence it is kind of ignored while computing the term weight, but it can also be replaced with some prior probability like the page rank of the particular document, which indicates the importance of this document. This portion probability of P W given D is approximated using MLE, and this is also the MLE, estimation of the query in the document. So it is basically the language model based similarity score as well, roughly, approximately. So as an extension of RM3 model, we also discussed RM1 model. As an extension of RM1 model, we also discussed RM3, which is a mixture model of this RM1. We have discussed RM1, but as we have discussed, RM2 can also be mixed with the query likelihood model. RM2, where the way RM2 is designed is basically here we are considering an IID sampling. In RM2 model, they considered basically a conditional sampling. So I haven't discussed that RM2 model here in this in the last class, because it is already shown that RM1 is much more superior than using RM2. So an extension of RM1 is basically RM3, where we linearly interpolate the RLM or RM1 model. This is also can be referred to as RM1. Basically, we are considering RM1 here with the query likelihood model, where alpha is basically the query basically the linear interpolation parameter. So specifically, the way this probability of the individual word will be being generated from the relevance model is approximated using this, where PW given R is basically the same formula that we have written here, where, as you can see, I have explicitly excluded the probability of PD, or the prior probability of the selection of the document. So these are basically considered uniform. So for all document, it is basically ignored. Okay, and PW given this just the MLE of the query of the word in the query. So it is basically the term frequency of the word in the query divided by the length of the query. So in sum, RM3, what we are doing, so given a corpus, basically a set of documents, and a query that is having, say, a number of terms. First phase, what we do is, in the first step, we perform a retrieval using language model or any other retrieval model. Then we consider all the top, say, M document as pseudo-relevant, PRD, that is pseudo-relevant document. All the terms in this PRD is basically considered as a set as ET, expansion term, that is all terms of top M documents considered as potential expansion term. Then we calculate probability of P given R, not P prime, P given R for each W in ET based on this formula, which is basically the RM1 model. And then we consider the top N number of terms from this ET having the highest PW given R. And then finally, for only those N terms, we linearly interpolate the derived density function here with the query likelihood model. Okay. Now, the obvious question is how we can implement this RM3 model. Okay. So first, let me write this RM1 model here. So PW given R equals to it is summation over all document D in, say, M number of top retrieved document, probability of W given D into the product over all terms in the query, how likely that the query term will be generated from the document. So this was the RM1 model. Note that this is the RM1 model. Okay. Now let's take a step backward. So what is our ultimate target? Our ultimate target is that given we have a query or something, 1, 2, 3, k number of terms, I don't know how many. First, so step 1 is not 2. Let's say step 1 is perform a retrieval. Step 2 is, say, PRD equals to top, say, M ranked document. Okay, this is PRD. Then let's consider step 3 is basically, as I was writing as ET, or I can write it as a PET, potential expansion term, as basically all terms in PRD. So let's consider the top M document. Let's say the value of M is, say, 10. Let's consider m equals to 10. That means after performing the retrieval, we'll be considering the top 10 ranked document and consider all the terms in those top 10 ranked document as the potential expansion term. That is, they have the potential to be an expansion term in order to perform a query expansion. Note that the initial query is containing say k term. Our ultimate target is to select more terms to be added to queue in order to make extended queue, that is expanded queue, and finally using those terms to perform the using together with the actual query, using those expansion terms to perform an extended retrieval. So basically step 4 of RM1 is compute probability of W given R following say equation 1. So let's call it equation 1. Equation 1 for all W in ET. Right? Just give me a minute. And then basically step 5 is consider top n terms having highest PW given R weight, this weight, and finally use those n terms as final expansion term. Final. As this is, I am considering final expansion term, this can be referred to as potential expansion term. Of course, ET can be containing, in this example, ET can be containing say maybe 2000 different terms, and from that we'll be computing this weight for all the terms in this ET, and then we'll be choosing the top n terms where the value of n can be say 50 or say 200. So more or less the range of n is set in between say 40 to 200, and the range of m is set from 10 to around 20 or maximum 30. And finally in step 7 we use this alpha. I mean, we compute this alpha into PW given R plus 1 minus alpha into probability of W given Q to compute to get the RM3 weight. RM3. So just write it here. Weight of W following RM3 is this. Now note that in this model altogether there are 3 parameters. Number 1, number 2, these are 2 RM1 parameter. This is number 3. So there are 3 parameters. So which are needed to be set. So the range in which m is varied is this, the range in which n is varied is this. So basically in this range, mostly the optimal value of n will be or m will be observed. and for alpha, the range is basically 0 to 1, mostly 0.1 to 0.9. This is the three parameters that are there in this RM3 model. Now the fun part, how we can implement this. That is, after performing an initial retrieval, how can we compute a set of, how can we get a set of terms as the potential expansion term? Oh, okay. So finally, the eighth step I just missed. The final step in this model is perform again re-retrieval with the n terms together with their weights. Consider together. So as we have discussed earlier, that term weighting is important to indicate the importance of the individual terms. So here the weight of the term is being set following this formula. All right. Now how we will be implementing this RM3? So let's just write a function, a very brief function. Define, say, so let's say, say RM3 term selection, the name of the function. We should take two parameters. One is the query, and second is basically the PRD. Now let me just not that straight. Never mind. So basically, Q is the initial query. PRD is basically set of M docs ranked at the top. So basically set of M top ranked document set of M docs ranked at the top after performing initial retrieval, after INIT retrieval. So this, how we can do, I hope from the PyLucine discussion, you can understand that while performing the search, we can, together with uh, the query object, we need to provide with the number of documents that we are providing to select. So we can provide this M here. So the first parameter is taken care of, right? That is the number of pseudo-relevant documents to be considered. All right. So based on that M document, what we need to do is we need to compute this. So basically, we are done up to this. So this is, so basically in this function, this RM3 term selection function, we are passing this as the first parameter and we are passing this as the second parameter. All right. So in this function, what we should be doing is, so first of all, let's consider let's consider similar to the way we have defined here. Let's consider ET equals to all terms of PRD. Note that PRD is a set. This is set of M terms. Set of M docs. Note that PRD is a set which is containing multiple documents. ET here is basically all the terms from those pseudo-relevant documents. All terms of PRD. How can we get that? I'll be discussing that in a bit. So let's say we have extracted all the terms from that PRD, from all the top rank documents, top rank M documents. Then what we need to do is, let me just to keep ourselves always in the loop. Let's just copy this thing. Oh, copy will be actually problematic. Let's just write it. Our ultimate target is to compute first PW given R, which is summation over all. So let's write capital D in M, probability of W given D into product over all query terms, probability of Q given D. This is our final target, not the final target, but the first target. After that, we'll be using the linear interpolation here with the query likelihood model. After getting this all terms from the PRD, what we need to do is we need to consider for all, no, or right, for each W. So for each W in ET, what we'll be doing is we'll be basically considering. So for each W, we need to perform a summation over all the documents in this PRD. So there we need to have another for loop for each. I'm writing a small d here, which was capital D here, for each D in PRD. Okay. Then for each PRD, we need to compute two things. Number one, PW given that D. For this D, what is the likelihood that this term that I am presently considering is generated? This is number one. Number two that I need to generate or I need to compute is basically the product over all query terms, probability of the generation of the query term from the document. Right? So let's do one by one. So for each D in PRD, what we need to do is we need to perform first this computation of this PWD. So let's compute that using somehow, let's say we have a variable which is called P underscore W underscore D, which is basically will be the maximum likelihood estimate of the word W in the document D. So this is basically this. The way we'll be implementing this or approximating this probability generation is using MLE, maximum likelihood estimate, considering D having set of balls, basically an urn. What is the probability that if I draw a term out of this urn, I'll be observing W? So it is basically the turn frequency of W comma D by the length of the document, right? So P underscore W underscore D is set with this value. Now what we need to do is for each query term we need to perform this. So this will be basically inside this for loop. So for each small q in capital Q, again, what we need to do is we need to compute their MLE. So MLE, sorry, MLE of the query term in the document. So basically, again, this is also approximated using MLE. Basically, term frequency of the query term in the document divided by the document length. Sorry, this will be good. So let's stick to the D convention, small d convention here. All right. This is again basically MLE. Now note that for each we need to basically consider their product, isn't it? So what we need to do is we need to store it somewhere which is initialized to 1. So let's declare basically a variable here, which is, let's say, probability of Q. So let's call it a probability of Q, which is initialized to 1. Okay. Now this will be for each Q in Q, probability of Q equals to probability of Q into MLE of the new term. So which is basically we can write probability of Q star equals to MLE of QB. So this thing is done. Now here for the word we need to perform this for all the documents. Now, okay, this thing is still not done actually. Sorry. So at present PQ is containing this component and PWD is containing this component for a single document. Right? So after this, what we need to do is we need to basically store the final, let's call it final, oh, not final, let's call it a P W given R. This equals to basically P W given D into P Q. Now this needs to be considered for all the documents, right? So what we need to do is for each word, we need to initialize a P W given R. For each of them, we should initialize it with 0. So for each word, so finally, after I should not be closing this bracket here. So here after this, so basically, I mean, if this for loop is completed, that means for a single term from this expansion term, potential expansion term set, for a single term, we have completed the computation of this thing. So basically, we have computed the computation. So basically, what we have done is for one term, we have computed its PW given R. So we can actually store that in a dictionary maybe. So let's call it say dict weight, or let's call it only weight or term weight maybe, where the key will be the word and the value will be its PW given R value. So for each word, I'll be setting this. So at the end of this function, if I return the weight, so this weight is basically, I should not be returning the weight because still it is RM1 term selection is done. So I should not be closing this here because I'm considering it's an RM3 term selection. So this is RM1 term selection is done. Not term selection is done, but term weighting is done. Okay. Now, what we need to do is we need to sort this weight dictionary, or I mean, in order to sort them, we need to basically convert it into a list. Then it is easier to sort. So what we need to do is sort weight based on the PW given R, this weight, this probability, based on this probability. Then select top n terms having highest weight, having highest PW given R value. So after this, so after the completion of this, now we have selected a set of n terms based on their weight or based on their importance, or particularly mathematically based on their PW given R value. Up to this, is there any question how we can do the implementation? Okay, then the next thing is, so basically now weight is sorted. And the next thing is, what we need to do is, we need to now again, so let's consider sorted underscore W is the say top n terms with weight, with the weights, top n terms with the weights, and based on their weights as well. So basically in this sorted W, there are two things that is stored. Number one is the term itself. Number two is basically the P, the term given our probability. These two things are stored, and this is sorted based on the PW given R value. So now what we need to do is, as I hope you remember, so this is basically sorted W is basically based on RM1. Now, in order to make this RM3, what we need to do is we may consider P prime W given R, this is RM3 weight, equals to alpha into PW given R, the RM1 weight, plus 1 minus alpha into probability of W given Q. Note that this function is not closed. So what we have is Q as a parameter. So far, we have used Q only to compute this part. Another thing is still needed to be done with Q is approximating this. So the next statement that I'll be doing is basically performing this linear interpolation. Here, note that the M is not passed as a parameter because PRD is basically a set of M documents. So after performing the search, it is implicitly, I mean, without mentioning, I am just selecting the top M documents here. And the top, from that, we are also selecting the top N terms, which is basically a parameter here. And here, sorted, after getting this sorted W, sorted weights or sorted words, what we need to do is, based on a parameter here, what we need to do is, first of all, we need to compute this. So again, as you can see, this is closed here. Now here, what we need to do is, for each W in, note that earlier it was in ET, say 2000 terms. Here it is for each W in sorted W. Note that in the sorted W, there are N words because top N terms are only selected. So for each W in sorted W, what we need to do is, this will be computed for only those N terms. What we'll be doing is, let's consider the final weight, a parameter, variable here. So final W or final weight, let's call it final weight, which will be containing the value. But before setting that, we need to compute this as well. So this is again, this is term frequency of the word in the query divided by query length, basically MLE. So final weight will be equals to some parameter alpha into PW given R. Note that PW given R is already sorted, stored here. So alpha into sorted underscore W in bracket, basically the, we can just the PW given R. So this is basically indicating the weight of the term W based on RM1, which is stored in the sorted W, plus 1 minus alpha. So this part is done, plus 1 minus alpha into MLE of the word W in the query field. That's it. This will be the final weight of each of the words. So we can consider final weight of W equals to this. Then in this function, from this function, we can return the final weight. Final weight. This is basically a, you can consider this as a dictionary or something like that, which is basically containing again two things. Two things it is storing. Number one is the term, which will be the expansion term. Number two, it is storing the weight or the importance. which is basically the expansion weight. So this is the end of this function. End of this function. Any question up to this? Now, an obvious question that you can ask is how to actually get this. One simple thing is, this is what? This is basically the turn frequency of the word W in D divided by T. So as we have mentioned, during indexing, creation of the inverted index, we first started with storing only 0 and 1. Then we stored the turn frequency. Then we stored the basically the maximum likelihood estimate as well. So basically, when we are making the inverted index, we can store this value in the inverted index. So for each term W, we'll be storing the doc ID, say DI, together with the MLE of W in DI can be stored in the inverted index. So this is basically the dict, the dictionary, and this is basically the postings. This is a single entry, 2 values are stored, and that's it. So just what we need to do is in order to get this, we just need to get the corresponding inverted index, this entry, and from there we need to search for this T here in this linked list, and we'll be getting this MLE directly. Now MLE of Q comma D is also can be retrieved from here, because Q is what? Essentially a word, essentially a W. So again, for Q, it is actually a word in the dictionary. So for the same document, so the thing is, earlier we need to, based on the word we are selecting the document. For here, in that particular document, we are computing, we are checking the presence of the document, presence of the query term. Again, I'm repeating, in the first place, here, first we are selecting W, then we are computing the MLE of W in D. Here, the D is selected, but Q is something else. Q is inside. So we are basically computing or checking in that document the MLE of Q. And that's it. So this is something that is very useful in order to implement this. One thing I must say, that here in this model, let me write the equation once again. PW given R, summation over all, say small d I am writing, name, probability of W given D, input product over all Q in probability of Q given D. This is PF of W in Q, D by D. This is turn frequency of Q in D by D. Note that there is no IDF factor in this RM1 model or even in the RM3 model as well. So that is the reason RM3 and also RM1 select, this is basically a drawback of RM3 model, select common terms as the expansion terms. This is a drawback. drawback of this RM3 model or RM1 model. This is RM1. Similarly, for RM3, if I just write the RM3 equation, it is similar. Just P prime W given R equals to alpha into PW given R, which is this function, plus 1 minus alpha into probability of sorry, W given Q. Again, this is term frequency of W comma Q divided by the length of Q. Still, there is no IDF. As there is no IDF, it selects pretty common terms as potential expansion terms. This is a drawback of RM3 and RM1. So, in order to address that, there are some works where this this IDF is explicitly inserted into this model, but the vanilla model, the vanilla RM1 or RM3 is actually suffers from this this problem of selection of very common terms as expansion terms. So finally, what we will be doing is using this, as we have said, returning of this final weight, which is containing the term expansion term as well as the expansion weight. What we will be doing is we'll be using those terms as the actual expansion term, and based on that we'll be basically perform re-retrieval with Q, the original query, plus, or in RM3 Q is already incorporated, basically with this final weight, final underscore weight, the term of that. So using this term, the weight, the term selected in the term stored in this final weight function as the expansion term to perform the final retrieval. That's it. Any question? This is a very important concept on how to implement this, because in standard information retrieval system like Lucene, this RM3 or RM1 or the ROQ is not actually implemented like BM25 or language model. In order to use them, we need to implement them on our own. So that's why in today's discussion, we presented how we can actually implement them formally from the programming point of view in a system like Lucene.